The second topic we want to cover in this lecture is a minimum spanning tree. So given a weighted graph, so that means every edge has a weight associated with it. We want to find a minimum weight set of edges that all connect all the nodes to form a tree. So essentially we want to connect everything together, and we want the total edge weight is minimum. So assuming that the weights are positive, then this must be a tree, because if we have more edges than a tree, we can always remove one, and still everything is connected. So this is known as minimum spanning tree. There are two commonly used efficient algorithm to find the minimum spanning tree: Prim's algorithm and Kruskal's algorithm. Here we're going to cover both. So Kruskal's algorithm uses the unifying data structure. So it essentially processes all the edges. So this is an algorithm where it's easy to deal with the data structure, where to deal with the graph representation where all the edges are in an array. So essentially that's what we want for this algorithm, is the graph represented as an array of edges. So we first sort the edges, and by increasing weight, so that the first one is the smallest weight, and so on. So then we start from the beginning. So we will take the edge that has the lowest weight, and each time when we take a new edge, we will check whether this edge will connect the two nodes that are not already connected. If they're not, we will going to add this edge. If this edge connect two nodes that are already connected, then we will just discard this edge. So in order to support this efficiently determine whether two nodes are already connected, and also connect them when they are not already connected, this is where we use the unifying data structure that we talked about earlier. So we will repeat until all the nodes are in the tree. So essentially, when we connect two nodes, we can check whether the resulting connected component, how many nodes there are. So if the number of nodes is equal to the total number of nodes in the graph, then we're done. But of course, we can also just go through all the edges, and then we'll also be done. So in the worst case, we will need to go through all the edges. So the complexity is E times log n, where E is the number of edges and n is number of nodes. So some of you might say, well, the first step of sorting the edges is already E log E, but E is at most n squared. So E log E is at most 2E log n. So when using the big O notation, we ignore the constant, so it's still big O E times log n. So also so that's basically where this E log n come from, because the unifying part give us essentially constant time for union and find. So that's the Kruskal algorithm. The other algorithm is the Prim's algorithm. So this algorithm will maintain a discovered portion. So in Kruskal's in the previous Kruskal algorithm, we sort of construct the tree kind of in a more distributed fashion. So we'll connect an edge here, connect an edge there. Eventually, they will all be connected. Prim's algorithm works differently. We will start from one node, and then we will gradually extend that to keep adding new nodes to this connected portion. So we will always maintain a connected portion or discovered portion. Initially, that will just be a single node. So we can pick an arbitrary node to start, because that node has to be connected to the minimum spanning tree anyway. So we start from that, and then we maintain distance of every other node to the discovered portion. So initially, all the other nodes have sort of infinity distance. And then when we process this node, we will check all the nodes that it connects. And if these nodes gives a lower cost connection, then we will update the weight. So every time we will find the nodes with the smallest known distance to the discovered portion, and then we will add that, and then we will update other nodes distance to the connected portion using the new node if we need to. So the naive implementation of this method will have quadratic complexity, because every time we will go through the end nodes and figure out what is their distance to the connected portion. However, if we use a priority queue, then we can drop the complexity to E log V, similar to the essentially the same complexity as the Kruskal algorithm. So here is a sort of a pseudocode for the Prim's algorithm. So we will start from A, and the distance. So after we look at A, we have a distance B and H are 4 and 8. So then we will B will have a smallest weight. We will add B, and because B's distance to H is 11, so that's 8 is still the shortest distance. So then C now have a distance of 8, and I think at this point we can choose either C or H. Either way will be equivalent. So if we choose C, and then I will have a distance 2 to the connected portion of ABC, then the F will have a distance of 4, and D will have distance of 7. So then the next one we will add is I, and so on. So this is the pseudocode for the Prim's algorithm. Each time we will extract the minimum from the queue. So this is a sort of priority queue. We will take the element with the minimum value. So that is the node that has the smallest distance to the discovered portion. And then given this U node, then we will look at all its neighbors, and we will see whether that neighbor's current distance is greater than the weight on the edge U to V. So if that current distance is bigger, then we need to update that. So we need to update the key value to be the edge weight. So this v dot pi part is used when we want to reconstruct the tree, in addition to computing the weight. So that's just maintaining the information that we are using VU to connect V to U. So that's it. And next time we're going to look at the problems using minimum spanning tree.